Socratic Math Tutor here. Today we're going to work on this integral. So specifically, we're going to do the integral from -1 to 0 of 1 plus x over the square root of 1 minus x dx. And it's always a good idea to give the thing you're integrating a name. So let's let, it's a hard sentence, let's let I equal this. And this is honestly a pretty easy problem. And the trick is really just to notice that this, the integrand, is in a very specific form. So in particular, it's a polynomial over a linear term, mx plus c, raised to the power of r. And in general, anytime you see an integrand like this, it's super easy to do the integral. Super easy to do the integral. And all you do is you let u equal mx plus c. So if you let u equal the linear term, you're going to find that this integral is not hard at all. But surprisingly, actually, a lot of people, according to the examiner's report, a lot of people got this wrong. So before going on with the solution, let's spend a moment just talking about what not to do. So here's what people did that was a mistake. They looked at this 1 plus x, and they said, okay, this is fantastic. I can break up the problem. I'm going to put the 1 here and the x here. I'm going to integrate this, integrate that, put our terminals in. There we are. Get the dx going. Get our denominator going. And there we are. You know, we've broken up the problem into two integrals. All we have to do is add these, work them out separately, and then add the results, and we'll be done. And logically, that works. I mean, if you actually did that, you would get the correct answer. But the problem is, you're increasing the amount of work you have to do by a considerable margin. In fact, I think you're basically doubling the amount of work you need to do. And so the dead giveaway that you've made a misstep here, if you've written down this sum of integrals and you're not sure if you should keep going or if you should backtrack, the dead giveaway that tells you that you should backtrack is this. So in this first integral here, to solve it, we're probably going to let u equal 1 minus x because, that's here. So basically, because it's in the square root, our first guess will probably be, let u equal 1 minus x. And then we look over here and we see that we've got the same thing in a square root. So obviously we let u equal 1 minus x here. And so this is our substitution for this integral. We use the same substitution in this integral, and that's actually the giveaway. Whenever you're doing the same substitution in two different integrals that are being added together, especially if they have the same terminals, it's a dead giveaway that you're doing the wrong thing. I mean, this is pretty much never the right thing to be doing. Okay, so if you do find yourself in a situation like that, just scribble out everything you've done. Use an eraser if you use pencil, use whiteout if that's what you got, or even just scribble it out if you have to. Go back to the original integral and do a u substitution on the original integral, because that's gonna halve the amount of work you have to do. It's a much better idea to do it like that. So let's go ahead and do it. So we'll let u equal 1 minus x, and I'll get two columns going. So over here, I'm going to do u of my terminal, so u of 0 and u of -1. Let's work those out. Just a little tip with this kind of thing. See how the 0 is on top here? I've got a 0 on top and a -1 on the bottom. Keep them in the same order down here. So put the 0 on top and the -1 below. If you're just consistent about the order, you won't accidentally mix up the order of the terminals, all right? So that's just a general tip there. Let's go ahead and find u of 0. So we use this expression. U is 1 minus x. So therefore, u of 0 is 1 minus 0. This will become a 0. So I put 1. Oh, wrong. That's not the color I wanted. Let's do, okay, there we are. So 1 minus 0 here, which is obviously it's 1. Okay? It's 1. U of -1. Similarly, we just put the -1 in. We get 1 minus -1. Okay, that's obviously 2. And the way I tend to lay out these u substitutions is, so I do these terminals on the left-hand side, And then right next to them on the right-hand side, I do something else. So here's what I do. So the first thing I'm going to do here is just rearrange this line to make x the subject. So the new variable is originally on the left because we let u equal an expression that we were interested in. But we pretty much always want to rearrange this so that you know the original variable becomes the subject, and that's exactly what we're going to do here. Okay, so x equals 1 minus u is our next line. Hopefully it's pretty clear how I got between these two, but if it's not, let's just quickly work it out here. So u equals 1 minus x. We observed that 1 minus is its own inverse, and therefore I can move the 1 minus over on the next line. So 1 minus u equals x. And then using symmetry of equality, I just put x on the left, and there we have it. We've got x by itself, and that's what that is, okay? So there's really two steps going from here to there, but they're pretty easy steps. I think you should be able to do them in your head, okay? Okay, so we've got x equals 1 minus u, and then we want to differentiate dx equals negative du. And at this point, we're ready to go on with finding I. So I equals the integral from, and here's the advantage of keeping these in order. I basically just write them down as my terminals in the order they're written. So I put a 1 up high, I put a 2 down low, and then I've got to deal with this 1 plus x. So I'm going to write, down here, I'm going to write 1 plus, and we know x is 1 minus u. So I'll write 1 plus 1 minus u, like that, over the square root of u. Remember, the whole reason we chose this particular u was that it was this. So we don't need to think too carefully about this, what happens when we replace x, you know, when we replace x by 1 minus u in here. It has to be u because that's kind of what we chose, all right? So we've got this, so that's really good. I don't want to write dx here because I've got u's all here, so there's no sense in writing dx there. What we're going to do is we're going to use this formula, and we're going to replace dx by negative du. So this dx comes down here, and it becomes negative du. I'll just write du without a negative because the negative will look weird. And what I'll actually do is just put the negative out there just to make the expression look a little bit less strange. It just looks a little bit nicer that way. A little bit less confusing. Okay, now in the next step, I want to switch the order of these terminals. And to do that, I actually pick up a negative here. But because two negatives make a positive, we're not going to have a negative in the next line. So integral from 1 to 2 with no negative out here. There's just nothing out there at all. And then let's go ahead and simplify this. Okay, so in the numerator, we have 1 plus 1 minus u, which is 2 minus u. I'll rewrite the denominator as u to the power of half du. And let's draw a big arrow up here and continue the problem up here. A good general tip, because they want you to use, you know, the lines they've given you. Good general tip is to break up your working area into 2 or maybe even 3 columns. You know, just work through the problem here. And once you run out of space, just draw a big arrow and continue it here. And that way you're still using these lines they want you to use. And, you know, you won't run out of space doing that, okay? Let's get this big arrow going here. Equals, and I'm actually going to break up the integral at this point, okay? So what I said about not breaking up the integral earlier, that only applies if you haven't done your u substitution yet and you're planning to do one. If you don't need to do another substitution, you know, it's perfectly okay to break it up. In fact, in this context, I'd argue it's probably the right move. It's probably, you know, the easiest way to get ourselves closer to our goal. Okay, so let's continue. I'll pull the 2 out here, keep my terminals the same. The u to the power of a half becomes u to the power of negative a half. And that's just because we're moving it from a denominator essentially into a numerator. Du minus, now u over u to the half is just u to the half. So minus integral from 1 through to 2, u to the half du, excuse me. And we can go ahead and work these out. Pretty straightforward. One thing I will say is keep in mind when integrating that step 1 is to raise this, to add 1 to that numerator, and then step 2 is to put it into the denominator. Sorry, what I've drawn makes absolutely no sense. Step 2 is to put it into the denominator. So first we add 1, and then we stick the result into the denominator. Okay, so for example, with u to the power of negative a half, first I add 1 to get u to the power of a half, and then I put a half into the denominator. So putting the number into the denominator occurs second. Try to keep that in mind. Similarly here, u to the power of a half is going to become u to the 3 over 2, and then I put 3 over 2 into a denominator, and that's how we proceed there. Okay. Now, for this next bit, I'm going to pull out these denominators. Okay, so basically, when you pull a fraction out of a denominator, it's going to flip upside down. Half is going to become 2. 3 over 2 will become 2 over 3. Okay, so half becomes 2, multiplies by 2, we get 4. I'll leave the u to the power of a half in here for now. Minus the 3 over 2 comes out, becomes 2/3. Leave that in there. And now we'll put the numbers in. It's 2 to the power of a half, minus 1. Then we've got our 2/3. Once again here, I'll put my terminals in. I could write here 2 to the power of 3 over 2. But 2 to the power of 3 over 2 is actually 2 root 2. It's kind of year 10 math. You should understand how that works. If you don't, just pause the video, have a little think about it, and maybe revise some year 10 exponents if you have trouble with that kind of thing. But I'm just going to go straight to 2 root 2 here, minus 1 there. And in fact, I think it might actually be a little bit more consistent to put root 2 there. Okay. Now, just looking over here at the form they want the answer in, you can see it's some number times the square root of another number plus a final bit. Okay, this square root is obviously square root of 2. We can see that just by looking at what we've got here. We've got some square root of 2's here. And so what we want to do is we want to expand these brackets out. We're going to bring all our square root of 2's together, and then our constants will go on the end. And those constants will become the c, and the coefficient of square root of 2 will become our a here. Okay? So we need to expand this out. We get 4 root 2 here, minus 4 rather. Minus, now 2 over 3 times 2 is 4 over 3. And then I'll add 2 over 3 right at the end. Let's bring our square root of 2's together, just like we were planning to earlier. Just like that, we get our constants right at the end. Minus 4 plus 2 over 3. I'm actually going to write minus 2 over 3 and put these in brackets. We'll be less likely to make mistakes if we take that step. And here, we just want to put things over a common denominator. So 4 becomes 12 over 3. So 12 minus 4 over 3 root 2 minus, once again here, we want to go over a common denominator. 12 minus 2 over 3 is what we get. And at this point, we're basically done. So the final answer, and because I've run out of space, I'll just write it up here. The final answer is going to be 8 over 3. Man, my arrow really didn't point to where I was going to write. It's going to be 8 over 3 root 2. Minus 10 over 3. And this is a complete answer, and you really should get full marks for that. I don't think there's anything missing in that working.